Hi everyone, welcome to this video where we'll be going through a fully worked out implementation of the FFT algorithm and how we can use it to solve a sample problem, which in our case will be polynomial multiplication. So without further ado, let's jump right into it. So this is what the problem we have looks like. So we have two polynomials, p of x and q of x. So p of x is 1 plus 2x plus 3x squared, which we can also write in this vector form as a sort of coefficient representation of the polynomial. So we'll write it as this vector 1, 2, 3. And we have q of x, which is 2 plus 5x plus x squared. Similarly, we can write it in this vector in coefficient notation as 2, 5, 1. So and the vector is arranged in ascending order of the degree of the corresponding term of the coefficient. So yeah, so we have two coefficient representations of two polynomials, and we want to find the product of the two polynomials. So we want to find r which equals p times q, and we want to find the coefficients of the polynomial r. And just as an aside, this video might be fairly long. So by the time we come back to it, we might forget where we were coming from and what we expected our final answer to look like. So just as a sanity check, excuse me. I went through and did this computation beforehand, and the result of the computation of the polynomial p times q is this over here. So it's 3x to the fourth plus 17x cubed plus 17x squared plus 9x plus 2. So yeah, by the end of the video, we should be able to come back to this point and see if our fancy algorithm with FFT was able to give us the right answer for this polynomial multiplication or not. Okay, awesome. So let's say you're given this type of problem on a homework or an exam. How would you go about approaching it? So just as a refresher for how we use FFT in this class to help us speed up computation for polynomial multiplication. At a high level, the algorithm looks something like this. So we start out with p and q in coefficient representation. So that's where we are now. We have p and q in coefficient representation, as I wrote up here. So what are we going to do from that point? So we're going to apply the FFT algorithm. And what the FFT algorithm is going to let us do is it's going to let us take, it's going to let us convert P and Q from coefficient representation to something called value representation. And value representation of P and Q is nothing but the polynomials P and Q evaluated at a certain number of points. So we're going to get the values of P and Q when we evaluate them at some points. And this sort of duality between the coefficient representation and the value representation relies on this statement that you've learned from CS70, which is that if we have a polynomial with degree n, then we need at most if we have a polynomial of degree n, then with at least n plus 1 points, we can uniquely identify the polynomial just from those n plus 1 points. So yeah, using that statement, we can show that given P and Q in coefficient representation and P and Q in value representation, we can convert one to the other as long as we have enough points. Okay, so yeah, this is the magic of FFT, but at a high level, all it's doing is it's letting us go from P and Q in the form of coefficients, like we have up here, 1, 2, 3 coefficient representation, and giving us the values of P and Q at endpoints. So we'll get P of x of 0, P of x of 1, and all the way until P of x sub n minus 1, where x0, x1, x to n minus 1 are all just points. Okay, so now that we've used FFT on both P and Q to give us value representation, this is the easy part. So in order to compute the result of the multiplication P times Q, which is R, what we can do is we can multiply the values that we got for both P and Q at the points that we computed, x0, x1, all the way through xn minus 1, and just multiply them together. So what happens when we do that? Well, we'll get that P times Q of x is equal to P of x times Q of x. This is just a fact that you can easily verify. So once we take at all of these endpoints, if we just multiply each of these points together, take P of x0 times Q of x0, and so on, we'll get the value of the multiplied polynomial at those same endpoints. So that's the second step. So the first step is the FFT that goes, let's go to value representation. The second step is the pairwise multiplication that gives us endpoints where we've evaluated the polynomial R, just P times Q. And then the third step is going from the value representation of the multiplied polynomial to the coefficient representation, which is sort of what we expect when we think of polynomials. We like to think of polynomials in terms of like coefficients and their corresponding terms that the coefficients are multiplied to. So that's the third step, which is interpolating back to the coefficient representation of the multiplied polynomial, and then we're done. So yeah, and I know that seems pretty convoluted for a fairly simple process, but you'll see how at each of these steps we're actually reusing prior computations and being efficient and clever in the way that we're designing the algorithm in the way that we weren't doing if we just FOIL out the two polynomials and when we're multiplying them together. So in the long run, this algorithm is indeed faster, even if it doesn't immediately look like it. Okay, cool. So now that we have three distinct steps for us to follow, let's just go through and start implementing it. Let's see what this. Let's take a crack at it. Let's see what it looks like. So in the first step, where we're computing the value representation of the polynomials P and Q, there's one very important thing that we need to decide. So we need to decide at how many points do we need to evaluate P and Q such that we can get a good value representation of the P times Q polynomial. So I'll write that down. So we need to evaluate P and Q at n points. So at this very first stage, we need to figure out what n is going to be. And something to note for this is that again, going back to the theorem that I mentioned before, with a polynomial of degree n, we need at least n+1 points in order to guarantee that we can uniquely identify the polynomial with those n+1 points. So if you think of the polynomial that we're actually trying to identify, that's P times Q, right? That's the whole reason why we're doing this computation in the first place. So we need we need to have enough points such that we can uniquely reconstruct P times Q. So let's think of what the degree of P times Q is going to be. Well, we know that P has degree 2, which is this x squared term, and we know that Q also has degree 2. So the degree of P times Q is going to be 4. I'm just going to write that down. So degree of R, which is the degree of P plus degree of Q, is going to be 4. But be careful, because we know that the degree of R is going to be 4, but we need at least 5 points, which is, again, n plus 1, or 1 more than the degree, in order to uniquely identify or uniquely reconstruct the polynomial. So we need at least 5 points. And the second thing to note is that for the FFT algorithm, we need the number of points that we're evaluating our two polynomials at to be a multiple of 2. Excuse me. So you'll see why that's the case in just a second. But essentially, at every step of the recursion, we need to be able to exactly subdivide our problems into 2 parts. And that has to hold true all the way down to the very base layer. So because of that, the number of points that we have also has to be a power of 2. Okay, so let's put those two things together. So we have that n has to be a power of 2, specifically the smallest power of 2. So it has to be the smallest power of 2 that is greater than the degree of R, because again, it has to be at least degree of R plus 1, which is the minimum number of points that we need. So it has to be at least, it has to be greater than degree of R, which is the same as degree P plus degree Q. Okay, so with this in mind, the smallest power of 2 that's greater than 4 is 8. So we have that n equals 8. Yeah, so let's write that out. What does that mean? So that means we need to evaluate P and Q at 8 points. And for this, we're going to need to use the 8th roots of unity. So 8th roots of unity. So you all know from lecture that in the FFT algorithm, we use these special points that are called the 8th roots of unity. If you need a bit of refresher on complex numbers, I suggest you check out discussion 2, question 2. It has a lot of good practice problems that'll help you gain a solid intuition for complex numbers if you aren't quite there at this point. But for now, all you really need to know is that these 8th roots of unity are all unique, distinct numbers. So they're just any old numbers that we can evaluate P and Q at, just like any other numbers. And they have a few really cool special properties that allow us to break down our recursion very, very smoothly and with no hiccups at all. And I'll get to those properties in just 1 second. But yeah, apart from those like special properties that allow us to have a really smooth recursion, there's nothing really there's nothing more special about these roots of unity for this specific problem. Okay, so yeah, with that in mind, I'm going to define this variable that I'm going to call omega naught. And I'm going to define that to be e to the 2 pi I over 8. And this is going to be the primitive 8th root of unity. And the reason I'm calling this omega naught instead of omega, you'll see when I get to the second half of the video. But I'm because omega naught is going to be a constant for the rest of the video. I'm just going to declare it right here. Okay. So now what I want to do is rewrite the problem as a matrix formulation that might seem a little bit unintuitive at first, but you'll see how it actually makes the problem a lot easier to understand, and it also allows us to see the recursive nature of the problem very, very effectively. So I'm going to rewrite the problem as this. So I'm going to write this initial vector here, which is the polynomial p evaluated at our 8 roots of unity. So we have the, excuse me, this should not be, this should be omega 0 to the 1, omega 0 squared, p of omega 0 cubed, p of omega 0 to the 4th, p of omega 0 to the 5th, and so on. I'm just going to write this all out. P of omega 0 to the 7th. Okay, so we now have 8 points, which is, again, what we decided our n was going to be. And yeah, each of these points, 1, omega 0 to the 1, omega 0 squared, omega 0 cubed, these are all distinct points, and these are all 8th roots of unity. Okay, so these are the points that we want to evaluate the polynomial at. So this vector over here is going to be the result of our FFT, which again is the values of p. And these are the points that we've chosen that we want to find the values of p, corresponding values of p for. Okay, and I'm going to also write this other vector on the right over here, which is going to be 1, 2, 3, 0, 0, 0, 0, 0. And this vector over here is nothing more than the coefficient representation of p. So this thing over here that I wrote earlier, I'm just expanding that out to be an 8-dimensional vector. And the reason for that is because we have to evaluate the polynomial at 8 different points. So essentially, I'm zero padding this vector over here with zeros that don't actually change anything about the computation, but allows us to have this matrix multiplication of an 8 by 8 by 8 matrix. So yeah, just as a recap, this is sort of the coefficient of x to the 0. This is the coefficient of x. This is the coefficient of x squared, and then so on. Okay, so these are the coefficients of p. And then finally, we'll have this big matrix over here that we're going to define this matrix such that we can go from as input, we can take in the coefficients of p as some 8-dimensional vector, and we'll spit out the results of computing the FFT, which is the values of p at our 8 roots of unity. So this matrix over here, which I'm going to call M8, M8 because it's going to be an 8 by 8 matrix, and it's going to be M8 of omega naught because we'll construct this matrix around our omega naught over here. This matrix is going to be special because that's the matrix that's sort of doing all the magic of the FFT. So I'm going to pause the video here, and I'll take just a second to write out this matrix. Okay, so I've written out the matrix, which we call a Vandermonde matrix, and let's take a second to convince ourselves that this matrix reformulation is actually doing what we expect it to do, which is evaluating the polynomial p at these 8 different points. So let's see. So if we want to evaluate the polynomial p at the point x equals 1, so that's this first point over here. Let's go back to p. So when x equals 1, p of 1 is just going to be 1 plus 2 times 1 plus 3 times 1 squared, which is 1, which is going to be 6. And okay, let's go back to the matrix formulation here, and let's think of this first row, which is going to be p of 1, and indeed we do have that this first row is equal to 1 times 1 plus 1 times 2 plus 1 times 3, and then plus a bunch of zeros, but that's still going to be 1 plus 2 plus 3, which is 6. So at least for that point, our intuition does hold. And the same thing holds true for the rest of the points, because, for example, p of omega naught to the 1, which is just p of omega naught, well, that's going to be 1 times 1 plus 2 times 2 times 1 times 1 plus 2 times omega naught. Sorry, this is p of omega. Oops. This is p of omega naught. This is 1 plus 2 times omega naught plus 3 times omega naught squared, which is exactly what we're getting here. So this is 1 times 1, 1 times 1 plus 2 times omega naught plus 3 times omega naught squared, and so on. So hopefully that convinces you that this this polynomial sort of reformulation is nothing more than just a compact way of expressing the valuation of the polynomial at these specific points, which are the roots of unity. Okay, so now that we've convinced ourselves of that, we sort of reformulated the problem that we have at hand. So the entire sort of premise of FFT is now just find an efficient way to do this matrix multiplication. Yeah, because in this matrix over here, we have n squared terms. So just without any other sort of shortcuts, if we just do this multiplication, this multiplication is going to be at least in O of n squared, and that's sort of assuming that all of our additions and sort of internal multiplications all happen at a constant time. So even with that assumption, this multiplication is going to be in O of n squared, but we want to find some way that we can do it in O of n log n, and that's where the FFT algorithm is going to come into play. Okay, so yeah, now we know what our problem is, and I'm going to point out one quick thing before I jump into how FFT breaks down this problem recursively to actually do this evaluation, and that is going to be this fact. So I'm going to copy this, put it down here, and I'm going to add this over here. So these are rows of this matrix, 0 indexed, 0 through 7, and this is column K. 0, 1, 2, 3, 4, 5, 6, 7. And one thing that I want to point out is that the I, jth entry of this matrix is going to have the value omega sorry, I'm going to write this as j comma k because we're using I to represent the imaginary number. So the j comma kth entry is going to have the value omega to the jk. And we can see this just by picking any two numbers. Let's say we pick j equals 4, k equals 6. So at their intersection, which is this point over here, we indeed do have that. We do have that this entry is omega, or omega naught to the 24. So I can write that as omega naught. Yeah, so this fact is going to be extremely important for this sort of the restructuring that we're going to do of this matrix, and it allows us to still keep some sense of the structure of the matrix and exactly how we're breaking it down. Okay, so I'm going to now comes the fun part. Now comes the part where we're going to break down this matrix and reconstruct it to make our computation a little bit easier. So again, I'm going to pause the recording and I'll come back with the reconstructed matrix. Okay, so I've written out the matrix, the reformulated, restructured matrix. And in case it's not completely obvious what I did here, let me show you exactly what I did. So I took these columns, which are the even columns of this matrix over here. I took the even columns, so this one, this one, excuse me, this one, this one, this one, and this one. So 0, 2, 4, and 6, and sort of squish them together in the beginning of the matrix here. And I took the odd columns, 1, 3, 5, and 7, and placed those in the second, the right half of this matrix over here. And that's essentially all I did. So I sort of just switched around the order of the columns of the matrix. Why did I do that? Well, before I answer that question, let's first see, let's first convince ourselves that we can still use this modified matrix in our FFT computation. So given this matrix over here, let's copy this over down here. Well, even with this reformulated matrix, just going to change my pen color. Even with this reformulated matrix, we still have that P of 1, P of omega naught to the 1, P of omega naught squared, P of omega naught cubed. Let me move this down just slightly so it's aligned with the columns, with the rows there. P of omega naught to the 4th, P of omega naught to the 5th, P of omega naught to the 6th, and P of omega naught to the 7th. So I'm being a little bit tedious here, but just want to make sure we know exactly what we're doing. So we're trying to evaluate the points at these 8. And we're trying to evaluate the polynomial at these 8 points here. And remember, we did that by taking the coefficient representation of the polynomial and multiplying it by this massive van der Waals matrix. But since we rearranged the columns, we're also going to need to rearrange the coefficients for the coefficients times the columns to exactly match up in the order that they were in the original FFT formulation. So what we're going to have to do is we're going to have to take the very similar, exactly how we did previously. We're going to have to take the even terms of this vector over here and squish them first. So 1, 3, 0, 0. And remember, these were all the even ones. And the odd ones, which are 2, 0, 0, 0, we'll put those in the second half of the matrix. So again, these are the even termed coefficients and the odd termed coefficients, and we're just reordering those the same way that we reordered the coefficients of the van der Waals polynomial. Oops. Okay, so I think hopefully we can convince ourselves that by rearranging both the columns of the van der Waals matrix and the elements of our coefficient vector, we still maintain the same computation that we were doing before we rearranged any of the columns. Okay, so now there's just one final thing we need to do in order to understand the truly recursive structure of this sort of rearranged matrix. And that is, I've written that down here. And all that I did is that I took the second half of this matrix over here, this part. I just rewrote it as a constant, which in the case of for each row, that constant is going to be omega naught to the power of the row number. So for example, I'm just going to move this a little bit up here so we can easily compare the two. So for example, for this row over here, omega naught cubed, omega naught to the 5th, omega naught to the 7th. This is the same as the row of omega naught terms that we had in the left half of the row. So these ones over here, times an omega naught term. This term over here is omega naught times 1. This is omega naught times omega naught squared. This is omega naught times omega naught to the 4th, and so on. So yeah, just reformulating the right half of this matrix. So the odd columns as this omega naught constant, omega naught to some power, which is the omega naught to the number of the row, that constant term times the exact same row that we had in the left half of the matrix. So this and this, and this and that. So the left and right halves of the rows are the same, apart from again that constant omega naught to some power. Okay, so now we have all the tools that we need to really break down this matrix. So it's been a lot of waiting, a lot of setting up, but now let's actually get down to it. Okay, so the first thing that we can do is observe the following. So let's consider the top half. Oops. Let's consider the top half of this of the left half of the matrix, and this bottom half. Okay, and let's try to observe. Let's try to observe however much we can. So the first thing that we can note is that omega naught. So this term over here, this term and this term. Well, they look different as we've written it out right here, but in actuality, we know that omega naught is an 8th root of unity, and by definition, omega naught to the 8 equals 1. So that term, this term and this term are actually equal. And if we go through and compare more sort of one-to-one correspondences between this upper top left, this top left matrix and this bottom left matrix, we'll actually see that this entire matrix equals this bottom left matrix. Now, why is that? Is it just some coincidence, or do we plan it out to be that way? Well, the answer is that we planned it to be that way, and that's precisely the reason why we're using these complex roots of unity. And just to convince you a little bit more about this fact, let's actually take two elements, for example, these two that we compared before, and show why they're equal. So instead of taking any specific two elements, I'm just going to take two elements in general. So let's say we have omega to the 2jk. The reason why we can take 2jk is because we know that in the left half of these matrix, all of these columns are of the form 2 times k, because these are, again, the even columns, 0, 2, 4, 6. And the row is going to be j. So we know that the value in that entry is just omega to the row times column, so omega to the 2jk. And let's also consider omega to the 2j prime k, where we have j prime is equal to j plus n over 2. And yeah, all that means is that if the first element is on the 0th row, this row over here, then the second element that we're looking at is going to be on the 4th row. If the first element is on the 2nd row, then the second element is going to be on the 6th row. We're just sort of moving halfway down along the matrix into the bottom half of the matrix, but in the same corresponding position. So let's see what we get when we substitute in this expression for j prime into the value of that entry over here. So this is equal to omega to the 2j plus n over 2 times k, which is equal to omega to the 2jk times omega to the nk. And remember, what do we know about omega to the n? Where in our case, n is equal to 8, because that's the number of points that we're working with. Well, we know that omega to the n equals 1. So this is going to cancel, because this equals this equals 1. And we're left with omega to the j 2j prime k is equal to omega to the 2jk, which is exactly what we wanted to show. We wanted to show that we could take an element in the top half, in this sort of top quadrant, and take the corresponding element in the bottom quadrant and show that they were equal. Okay, so now that we've shown that specific equivalence, we can analyze the right half of the matrix too. We haven't forgotten about that one. So we already, what's cool about the way that we broke down the right half of the matrix as this sort of constant term times the same matrix that we had in the left side. So this is the exact same as what we had on the left side here. This is sort of a constant term that we're multiplying, but those this and this are the same. Similarly, this block is equal to this block and this block are the same, and we just have this sort of vector of constants that we're pairwise multiplying with each element of the block. Okay, so we already know that the pink block equals the blue block. So the only thing we have to consider now is how these constant terms that we're multiplying to each row, how do they affect the equation? Well, there's one main pattern that we can deduce from the constant terms. And again, it has to do with being in the bottom half or the top half of the matrix or the bottom half. So let's again, let's look at two constant terms. So let's look at this constant term and this constant term. Well, we have that omega naught to the sixth is equal to omega naught to the fourth times omega naught squared. And we know that omega naught to the eighth is 1. So omega naught to the fourth is actually going to be -1. And the easiest way to think about this, just as a sort of aside about complex numbers on the unit circle. This is complex plane, real imaginary. This is 1, -1, I, -I. So if this is this point is our omega naught, the easiest way to think about it is that when we do omega naught, when we calculate omega naught to the fourth, it's sort of 4 rounds of omega naught across the unit circle counterclockwise. So there's 1, there's another round here, another round, and another round. So after 4 rounds of omega naught, we're at the value -1. And in order to go back to 1, we have to do 4 more rounds. So this is going to be omega naught to the fifth, omega naught to the sixth, omega naught to the seventh, and finally omega naught to the eighth. So yeah, this explanation was not super rigorous, but again, if you want to if you want a little bit more intuition about complex numbers, I recommend checking out discussion 2, question 2. Okay, so now we know about that a little bit. We can actually consider we can consider these left and we can consider the top and bottom sort of constant terms a little bit separately. So we actually have that the top constant term, the sort of the top vector of constant terms, excuse me, is equal to negative the bottom vector of constant terms. Okay, so this is all nice and dandy, and we've shown that this matrix has basically a lot of repetitions. It's essentially 4 quadrants of the exact same submatrix with the right half being slightly modified. In particular, we have this extra sort of vector of constant terms that we're multiplying with each element of the quadrant, but apart from that, the quadrants are fairly similar. Okay, so now let's think of how we can use this repetition in the definition of the matrix to make our lives a lot easier. So again, remember that we want to compute the result of this product. So we have 1, 3, 0, 0, which are the even terms of the coefficients, and 2, 0, 0, 0, which are the odd terms. And now we can observe that in order to compute the top half, let's say we want to compute the top half of this matrix computation, this matrix multiplication, which is going to give us a vector. We want to compute the top half independently of the bottom half. So in particular, let's say we just want to compute for now p of 1, p of omega naught, p of omega naught squared, p of omega naught cubed. What is this going to be? Well, it's going to be, we know that this is going to be this matrix over here, our convenient purple matrix. That's sort of the building block of this entire matrix representation. So it's going to be that matrix, 1, 1, 1, 1, 1, 1, 1, omega naught squared, omega naught to the 4th, omega naught to the 6th, to the 4th, omega naught to the 6th, omega naught to the 6th, omega naught to the 12th, omega naught to the 12th, omega naught to the 18th. Okay. We know it's going to be this matrix. I'll move this down just slightly. This matrix times this top half of the vector that we're multiplying our coefficients with. So yeah, in particular, we have it's going to be equal to this top half of this vector. So these terms over here, 1, 3, 0, 0, plus this vector of coefficients, omega naught to the 0, omega naught to the 1, omega naught squared, omega naught cubed, pairwise multiplied by, and I'm using this x here as the symbol for pairwise multiplication. It's going to be pairwise multiplied by, I'm going to move these terms around a bit so we have more space. Pairwise multiplied by the same computation, but on the sort of taking our this building block matrix, and I'm going to move this down actually. Taking this building block matrix and multiplying it instead on the odd terms. And let's take a second to convince ourselves why this is the case. Well, for this specific row, we know for the first row, we know that what we have to do is we have to take this this first part of this top left matrix here, multiply it by take the dot product of that vector with this top half of this vector, and then yeah, for the second part we take this constant, multiply it by this vector, and take the dot product of that with this bottom half vector. And then we just add those two up, and we're done. That's the result of our FFT for the first row. And so, given that, it's fairly straightforward to generalize that to instead of just doing a dot product of two vectors, instead you're doing the multiplication of the entire matrix with the vector. But the idea is just the same. Instead of just the first row, we're now looking at all 4 rows together. Okay, and we can do something very similar with the bottom half of our polynomial matrix. This is equal to p of omega naught to the 4th, p of omega naught to the 5th, p of omega naught to the 6th, p of omega naught to the 7th. And this is sort of the beauty of this recursive approach is that I don't even need to rewrite much here. This is the exact same computation, except I'm just putting in a minus sign here before I'm subtracting the sort of the product of the vector of matrices with the product of our building block matrix with the odd elements. And why is that the case? Well, let's look at this again. So we showed that these terms over here were basically just the negatives of these top terms. But apart from that, everything else is the same. This matrix, because we know that this matrix and this matrix are the same as the purple matrices, and so everything else is the same, except for these terms. Over here, and for these terms, the only thing we have to do to change them is convert this positive sign into a negative sign, because that's enough to get the right terms. Okay, so I'm just going to write out subproblems that I'm going to highlight the subproblems that we actually need to compute, and all the other subproblems are just sort of copies of these two subproblems. So we need to compute this for sure, which is the product of our sort of building block matrix, this pink matrix over here, with the top half of our coefficients vector. And the top half, again, it's not the actual top half, it's the even terms, because this is the vector that we've rearranged in order to ease our computation. Okay, so we need to do that computation, and we need to do this computation, which is the same matrix. So these two matrices are the same, but this time it's multiplied with the odd coefficients, odd termed coefficients of our coefficient matrix. So our original coefficient matrix looks something like this: 1, 2, 3, 0, 0, 0, 0, 0. We have to do this subcomputation with this smaller matrix times the even terms plus some constant times the smaller matrix times the odd terms. And for the bottom half, it's again, as we said, we can pretty much reuse the exact same computation. So this first half here is the same as this one. These two are equal, and this bottom one is equal as well. Again, the only thing that was different for the bottom half of the computation was this negative sign that we flipped, because these terms are the negative of these terms. Okay. So that whole long-winded process, all that told us is that in order to compute this entire product of this Vandermonde matrix with this coefficients vector, we only need to do two subproblems of both exactly half the size in order to reconstruct the original matrix multiplication. So in order to reconstruct this combined vector of points, so we have the top half of the so we have 4 points that are evaluating using the top half of the matrix, 4 points evaluating using the bottom half. In order to combine those together, we just sort of have to stick those two vectors together. So that doesn't take much computation. Okay, so I'm going to write this a little bit more generally. And in order to do that, I'm going to first note that this sort of sub building block matrix that I've been referring to this whole time, we can actually rewrite it as M4 of omega naught squared. And why is that? Well, note that each term of this matrix is just what we would get with the original omega naught matrix. This matrix over here, omega naught squared, omega naught cubed, omega naught to the fourth, and so on. Except each term is just multiplied by 2. So in this case, omega naught squared, omega naught to the fourth, omega naught to the sixth, and so on. And specifically, the reason why that's the case is because all of these columns that we got this original matrix from were even columns, and the rows were still the same. So all of these terms were of the form omega naught to the 2jk, which is the same as omega naught to the jk squared. So squared. So all of these terms are just squares of the copies in the original van der Waals matrix. So yeah, we can rewrite this purple matrix here as M4 of omega naught squared, and the 4 is just because it's a 4 by 4 matrix this time. Okay, so I'm going to create this recursion tree of subproblems that we have to solve. And after we do this, it should be clear how this is very at its core a divide and conquer problem. So the main problem, the original problem that we wanted to solve was the product of the M8 of omega naught matrix, which is this 8 by 8 matrix over here. This is just the original M8 of omega naught matrix. We wanted to consider the product of that with our vector of coefficients, which was 1, 2, 3, 0, 0, 0, 0, 0. Okay, and in order to do that, we realized that there's 2 subproblems we need to solve, this orange one and this green one. And so those 2 subproblems were just, I'm going to box this. Those 2 subproblems were M4 of omega naught squared times 1, 3, 0, 0. So this one over here. And M4 of omega naught squared times 2, 0, 0, 0. Okay, so those are the 2 subproblems that we've split up our original problem to, and then there's some work that we have to do to combine those 2 subproblems together, but we won't include that here at this step. Well, why not break this down even further? And we can, because FFT is this recursive algorithm that relies on these subproblems to build up the original problem. So let's break this down even more. Let's take it to its logical conclusion. So this is going to look like so M2 of omega naught to the fourth, and in the left subproblem, we'll always take the even coefficients. So this is going to be 1 and 0 because they're the coefficients at indices 0 and 2. So it's going to be 1, 0 on this left-hand side, and M2 of omega naught to the fourth times 3, 0 on this right-hand side. And again, the way that we broke down this subproblem into these 2 subproblems, the exact same way as how we broke down this the original FFT problem into these 2 subproblems. Okay, so I think you see where this is going, but I'm just going to keep breaking down this FFT recursion tree. So this is equal to M2 of omega naught to the fourth times 2, 0, M2 of omega naught to the fourth times 0, 0. And let's just take it all the way down. So this is equal to m1 of omega naught to the 8 times just a single number 1. And this is equal to m1 of omega naught to the 8 times a single number 0. Similarly, this left subproblem is equal to m1 of omega naught to the 8 times 3. This one here is m1 times omega naught to the 8 times 0. So we have these two subproblems. And I'm running out of space a little bit, so I'm going to shrink this actually. So what I'm going to do is I'm going to just make these smaller. I'm going to move this along a little bit over here. And I'll make these smaller, and then I'm going to move them along. Okay, that's good. Okay, and then, yeah, the exact same thing on this side. I'm just writing this out for completion's sake. M1 of omega naught to the 8 times 2. M1 of omega naught to the 8 times 0. Okay, and finally, this is m1 times omega naught to the 8 times 0. m1 times omega naught to the 8, also times 0. Okay, so let's take a step back at this point and figure out what we need to do at this point. So from this point, we can pretty much break down. We can go down each of these subproblems that we've broken down the original subproblem to, and start at the very base, because we know that the base is a base case. We have these sort of just vectors with size 1, so we can very easily do the multiplication, and then using the technique that we have here for building these subproblems back together, we'll use that same technique to build out these subproblems. Okay, so let's do it. Okay, so I've gone through and just moved down and reproduced this recursion tree that we had written above. And as I mentioned before, let's go through starting at the very bottom layer, which is the base case, and build our way up to get our answer to the final to the main FFT problem. Okay, so the first thing to note is that m1 of omega naught to the 8. Well, again, omega naught is an 8th root of unity, so omega naught to the 8th is just 1. So this is just m1 of 1, which is just a matrix, a 1-by-1 matrix that looks like this. It's a 1-by-1 matrix with 1 as the only element. Okay, so all of these problems over here, so like all of these problems at the base layer, pretty much just end up being the matrix 1, which is m1 of omega naught to the 8 times whatever element we have that's being multiplied by m1 of omega naught to the 8. So I know it's a little bit hard to see, but essentially it's just the base layer is exactly just these terms. So I'm going to replace it and rewrite it over here, starting from the base layer. The base layer is just 1, 0, 3, 0, 2, 0, 0, 0. Okay, and that's the base layer. So that's good. We have a good amount of the computation. We have a good amount of the recursion already done. So the next thing to think about is how do we take these two subproblems and combine them back into a subproblem that's one level bigger, or like on the next level of the hierarchy. Well, remember, we know how to do that. What we have is that in our case, the resulting combined subproblem is going to be a vector of size 2, because each of these individual ones, these two subproblems were vectors of size 1. And we know that this combined subproblem is going to look something like this. So it's going to be the left matrix, which is the left subproblem, which is the matrix corresponding to vectors of size 2. It'll be that. So it's going to be that plus our omega naught, our omega constant vector times the second subproblem, 0. And the bottom half, or the bottom row, is going to be 0 minus our omega constant vector times, again, the right subproblem, which is 0. So this is a little bit confusing because you'll notice that I haven't included the omega naught underscore here. I'm just calling it just omega. And the reason for that is at different levels of the hierarchy, our omega, which is our sort of a vector of constants that we're going to multiply the right half of our, the right subproblem with, is going to be different. For example, at this level, all the omega naughts were omega naught to the 8. So in this case, our omega was equal to omega naught to the 8. But at this level of the subproblem, all the omega naughts were omega naught to the 4. So for when we're combining these subproblems, or when we're computing these subproblems, our omega is going to be omega naught to the 4th. And similarly, for this level, omega is going to be omega naught squared. And for the original subproblem, when we're combining these two subproblems together, the omega that we're going to use is just going to be the original omega naught. Okay, so with that in mind, we know that this is actually omega to the 4th, omega to the 4th times 0, and this is also omega to the 4th times to the power of 0. Excuse me. But luckily for in this specific case, it doesn't really change much, because both of these omegas, both of these constant terms are being multiplied by the right subproblem, which is just 0. Excuse me, this should be 1. Sorry about that. Yeah, so this is the left subproblem times omega, left subproblem plus omega times the right subproblem, and the bottom half is left subproblem minus the vector of constants pairwise multiplied by the right subproblem. Okay, so this is just 1 plus, again, 1 times 0, which is just 1. And this is also 1 minus 1 times 0. This is 1 minus 0, which is also 1. So when we combine these two vectors together, we just get a vector of 1, 1. And yeah, if you didn't quite follow that, this is a little bit confusing because the vectors are so small. But when we get to larger vectors, and especially when we're combining the main FFT subproblem, those two subproblems together, you'll see very clearly exactly how what the recursion looks like. So just bear with me for just a second. Similarly, we can combine, so let's look at this subproblem. Well, we know that it's going to be a very similar pattern. So it's just, again, it's the left subproblem, 3, left subproblem here as well, 3, and it's going to be the omega. So again, in this case, omega is equal to omega naught to the 4th. It's going to be the omega to the 0th constant vector term times the right subproblem, which is 0. It's pairwise multiplied. Sorry, I keep forgetting. And then minus omega naught pairwise multiplied with the right subproblem. So again, this just works out to 3 comma 3 because this is 3 plus 0, 3 minus 0. And actually similarly for all of these subproblems, because all of these have at least one 0 term in them. So all of these have a 0 term as the right subproblem, excuse me. So the vectors for these are actually just going to be the left subproblem repeated. So 1, 1, 3, 3, 2, 2, and for this case, it'll be 0, 0. Okay, so that's part of our, that's halfway through our recursion 3 done. We only have 3 more subproblems to go. So we need to now combine these 2 subproblems and also these 2 subproblems. Okay, so let's consider, and let's call this A, let's call this B. And A and B are just what we get when we combine those 2 subproblems together. Okay, so we have that. I'm going to erase this because I think this is, we've already gone through this, and I want to have this space right next to A and B so we can see what we're doing more clearly. Yeah, so for A, we know that we're combining 2 subproblems, each of length 2. So our resulting vector for A is going to have length 4. It's going to have 4 slots. And then we have to figure out what to put in those slots. Okay, so again, going back to what we did here, we're looking at the top half of the points that we're evaluating that specific polynomial at, which is the top half of our answer, pretty much, and the bottom half. So we'll split this vector up into 2 parts. So on the top half, we're taking the left subproblem, 1, 1, and we're adding it with this vector of constants that we're then pairwise multiplying with the right subproblem, which is 3, 3. And in the bottom half, this is equal to the vector, the left subproblem vector minus this vector of constants, omega constants, that are pairwise multiplied with this, with again the same 3, 3 right subproblem vector. And again, in this case, omega is equal to omega naught squared, because we're at the level of we're at this level of the hierarchy here. So the omega that we're using for omega constants is going to be omega naught squared, because the matrix that we're computing is in terms of omega naught squared. Okay, so let's go through and do this computation. It should be fairly straightforward. So this is 1 plus omega naught, omega to the 0, excuse me, which is 1. And so this is 1 times 3. So this is 1 plus 1 times 3, which is 1 plus 3, which is 4. This is going to be 4. And let's look at excuse me. Yes. Okay. So let's look at this computation. So this is 1 plus omega 1 plus omega to the 1 times 3. So 1 plus omega to the 1 times 3. Well, what's omega? We know that omega is omega naught squared. So this is equal to 1 plus omega naught squared times 3, which is the same. Well, we know that omega naught was, we know that omega naught is e to the 2 pi I over 8. We define that all the way up here. So omega naught squared is equal to e to the 2 pi I over 4, which is e to the pi I over 2. And when you simplify this complex number, you actually get I. I'll leave you to verify that computation. But yeah, so this second row in this vector actually ends up being 1 plus I squared. Sorry, excuse me. Omega naught squared was I. So this is 1 plus I times 3, which is just, 1 plus 3I. So that term is 1 plus 3I. Okay, and let's move through the rest of them. This is 1 minus 1 times 3. So this is 1 minus 3, which is minus 2. And similarly, this is 1 minus, well, omega to the 1. We know that omega to the 1 is the same as omega naught squared. And we know that omega naught squared is I. This is 1 minus I times 3, which is just 1 minus 3I. Okay, so that's this A subproblem here. So A is equal to this vector, which is 4, 1 plus 3I, minus 2, 1 minus 3I. Okay, almost there. 2 subproblems left. So now let's compute B. And B is going to look fairly similar. Or it's going to be very similar in terms of the sort of logic that we use. So for B, again, it's going to be a 4-element vector. And it's kind of a little bit hard to see here, but the 2 subproblems, the left subproblem is 2, 2, the right subproblem is 0, 0. So this expression that we have for computing the elements of B is going to look fairly similar. It's the left subproblem, which is 2, 2, 2, 2, plus this vector of constants, pairwise multiplied with the right subproblem, 0, 0. And the bottom half is the same vector, left vector minus the vector of constants, pairwise multiplied with the right subproblem. And in this case, our computation is a little bit easy because we know that this term is always going to be 0 because it's multiplied by the 0 vector. So this top half is just going to be 2, 2 plus the 0 vector, which is going to stay 2, 2. And similarly, this bottom half is going to be 2, 2 minus the 0 vector, which is also going to be 2, 2. So our B vector is actually all 2s. Okay. Yes, that's the second the second last layer of the computation done. So now we just have to combine these 2 subproblems. I'll call the combined subproblem C. And the combined subproblem C is actually going to be our original matrix computation that we wanted to do in the first place, which is M8 of omega naught times the entire vector of coefficients that we're using. Okay, so we know that C is going to be an 8-dimensional vector. So I'm going to leave some space for it. And we know, again, that it's going to be split into a bottom, a top sort of combined the combination of subproblems on the top and combination of subproblems on the bottom. So again, the left vector, the left subproblem for C is 4, 1 plus 3i minus 2, 1 minus 3i. So yeah, 4, 1 plus 3i minus 2, 1 minus 3i. And we're adding it to this vector of constants, omega naught, omega 1, omega squared, omega cubed, pairwise multiplied with the right subproblem, 2, 2, 2, 2. And the bottom half is going to be the same left subvector. So by this point, I think you get the drill, minus this vector of constants, omega naught, omega 1, omega to the 1, omega squared, omega cubed, pairwise multiplied with this, the right subproblem vector. And again, in this case, omega is actually equal to omega naught, because we're at this, the top half of we're at the very top of this recursion. And over there, we said that the omega that we're using in the formulation of the M8 matrix is actually going to be omega naught, not omega squared or omega to the fourth, just omega naught. So that's the omega that we'll be using. And yeah, the final thing that we have to do is just combine these two matrix formulations together. So I won't go through all the math, but this ends up looking something like this: plus I, 3 plus root 2, minus 2 plus I, 2I, excuse me, 1 minus root 2 plus I, root 2 minus 3, 4, 1 minus root 2 plus I, 3 minus root 2 minus 2 minus 2i, 1 plus root 2 plus I minus 3 minus root 2. So this looks a little bit complicated, but let's center ourselves a little bit. What is this C? What is the result? What are we actually computing? Well, C is just equal to the result of our FFT. C is, let's go back to the original thing that we wanted to compute, which is this M8 omega naught matrix times this vector of the coefficients of P. That's just the result of the FFT. So C, which is the result of the FFT, C is equal to P1, P omega naught to the 1, and so on, all the way to P omega naught to the n minus 1. Okay, so that's one of the FFTs done. And you can tell this has been a pretty long-winded process, and apologies if it got a little bit hard to follow at times, but all the essence of what we did there is just realize that we can break down our problem into smaller subproblems and then figure out a way how we can combine them together, and just going through and actually doing that and implementing that recursive algorithm. Okay, so I'm going to pause there, and I'm going to verify that using this FFT approach, we actually get the intended result for the polynomial. I won't go through and do the FFT for Q but I'll show you some code that proves that multiplying the matrices together and then getting the value representation, and then multiplying the corresponding points, and then going back and doing the interpolation into the coefficient representation gives us the correct polynomial. Hi everyone, welcome back. So yeah, just to conclude this video, I want to show you some code that goes through a little bit of what we did before, and sort of can help us wrap up this polynomial multiplication and show us that we actually do get the correct polynomial. So I'm going to start by defining omega to be the same omega naught that we were using before. This is using a Python library called SymPy. And essentially what it allows us to do is do symbolic calculations. So in Python, if you work with like exponents of like pi times I times like something, you're going to usually get like a bunch of messy, complicated floats that like basically take things like square root of 2 and replace them with like 1.414, so on. And what SymPy lets us do is it sort of lets us see, doesn't expand the square roots, so lets us make calculations and let us see like the unsimplified numbers behind them. Okay, and then M, I've constructed here is the Vandermonde matrix that we made before. So you can sort of imagine if square root of 2 over 2 plus square root of 2i over 2, this term here, this is just omega. So this is, yeah, this column is omega squared, omega cubed, omega to the 4th, and then so on. And you can convince yourself that this is the same Vandermonde matrix, M8 of omega naught that we were working with earlier. Yeah, and then P is a vector of the coefficients of the polynomial that we were working with. So this is very, very similar to what we did before. Yeah, and then the FFT of P, which we went through and that we had an hour-long video about. Essentially, it's just again, it's the Vandermonde matrix M8 of omega naught times the vector of the coefficients of the polynomial. And so over here, I'm doing this multiplication directly. I'm not doing it with FFT. I'm not doing it with the recursive approach that we used before, because we already went through and did that. But I just want to go through and show you that the calculation that we did before ended up being correct. And you can go and rewind the video and see that these numbers are the same as the ones that we got before. So again, FFT of P is the result of evaluating P at those 8 points, P0, P omega naught, P omega naught squared, all the way to P omega naught to the n minus 1. And then once we have the result of evaluating P at those 8 points, we want to go through and do the same thing for Q. So yeah, Q, if you remember, was this polynomial 2 plus 5x plus x squared. So this is the coefficient representation for Q. And then we take the same Vandermonde matrix because Q is also a length 8 vector. So we can take the same Vandermonde matrix of size 8 by 8 and multiply it by Q to get the result of evaluating Q at those same points, omega 1, omega naught squared, and so on. So the reason I chose P instead of Q is because Q is a lot more hairy, and you can see even though SymPy is trying to simplify this expression, it's having trouble because you have some 14th powers of terms divided by 128. So I just didn't want to mess with that. That's the FFT of Q, and then this is pretty cool. So this is what we're doing in that second step, which is that element-wise multiplication of like taking P of x, Q of x, multiplying them together to get the value of P times Q at that specific point x. That's all we're doing here. So we're taking the value of P at 1 is 6. the value of p at, the value of q at 1 is 8. And so the value of p times q at 1 is 48. Similarly, the value of p at omega naught is this term. The value of q at omega naught is this term. So the value of p times q at omega naught is the product of those two terms. So that's what this looks like, this vector here. And this vector, just as a reminder, is the value representation of the polynomial p times q. So it's the result of evaluating the polynomial p times q at those same 8 roots of unity that we've been using as points this whole time. Okay, and so this last part is the polynomial interpolation that I mentioned before. And I won't go through this in too much detail because I think this video has already gone pretty long. But in essence, for polynomial interpolation, you take the omega that you were using before, you invert it. So this is omega inverse. And then you construct a very similar Vandermonde matrix as we were using before, except instead of omega naught as sort of the base element that you're using to construct the entire Vandermonde matrix, you're using omega inverse. And you're also multiplying by 1 over 8 or 1 over n, where n is the size of the matrix. So the book has some proof about why you can use the FFT with this sort of inverted matrix and just do FFT using the inverted matrix and the value representation. So you take the inverted matrix, multiply it by the value representation of the p times q vector, and you'll get back the coefficient representation. So in normal FFT, we're going from coefficient to value. Here, we're going from value, multiplying by the inverted matrix, and then going to the coefficient representation. Yeah, the specific reason why we can use the inverse has to do with the fact that n and n minus 1 are co-prime. So there's like a one-to-one pairing between the multiplicative group centered around omega naught and the multiplicative group using omega naught inverse. But that's not very relevant for this class. All you really need to know is that the interpolation works. Okay, and so going back, doing the FFT, which is just taking this inverted matrix and multiplying it by this value representation of the polynomial p times q. So this is what the FFT interpolation actually is. It's just going from the value representation, multiplying it by the inverted M matrix to go to the coefficient representation. We get this very simple looking answer, which is 2, 9, 17, 17, 3, 0, 0, 0. And if you go back to the very beginning of the video when I pointed out what the correct answer should be, it turns out that it actually was it was this. So it was 2 plus 9x plus 17x squared plus 17x cubed plus 3x to the 4th. So yeah, hopefully that helps. Yeah, this is. So I tried to go through everything in as much sort of detail and excruciating detail and a lot of repetition as much as I could, just to ensure that everything was as clear as possible. But in case you still have any questions, feel free to leave any comments or make a private post on Piazza or yeah, something like that. So yeah, thanks for tuning in. Hope this was helpful. Thanks.